Hey guys, my name is Alex Britton and I'm doing my technical presentation on antennas and how they work. I'll show you how they work, the different types of them, and how we can use different types of antennas to benefit ourselves in the field with drones. So the first slide here I'll show you, it's just basically what is an antenna. So an antenna is a device that converts electrical energy as a solid copper wire, usually a copper wire, and makes an electromagnetic wave that sends out in the air where we can put information within that signal. So just a basic way of using it. So here you have a backup monitor for a car, and so what you have is you'll have a signal with a little receiver here that receives a signal from the transmitter, which comes from the camera, and the camera will send its signal to here, and the receiver here will accept it.
Okay, so now I'm going to show you how a basic antenna works, and we have a dipole antenna. So you have a positive wire and a negative wire, and it's called dipole because you have a positive and a negative, two wires in a pole. So here you'll have your current flowing from the positive down to your transmitter, and it'll be flowing out of the negative wire, the negative end of the wire, and flowing out. So for every single wire where there's electricity flowing through, there is an electromagnetic field. And so in between these two wires, the electromagnetic field cancels each other out. The current cancels each other out. But when you put an insulator there, it's good. So you have these 2 points here on both the ends to where you're not able to have this cancellation just because they're so far apart. And this is how most antennas work. So as you have this cancellation, this end is technically trying to get to this end. So what happens is it does this, makes this signal that starts out here and just goes over, and it just keeps going over, and it sends out a signal in both directions, going up here in this energy field, and also this energy field really goes down below also. And this is a basic omni, and up here you'll have higher voltage, and down here you have lower voltage. Up here you're going to have lower current, and here you're going to have higher current to come back down through and then complete it. And what we see today on most modern UAV antennas is this it's called a coaxial wire. This is a coaxial wire, and the type of antenna is called a coaxial antenna. So all you do is have your positive in the middle, and then you have your negative on the outside, and in between these two is an insulator. It insulates the two signals where there is no cancellation area. And so from here, really, it just flows up the top, goes around, and flows around and create a nice omnidirectional antenna.
Okay, so now we're going to look at the different types of antennas. So we have low gain omnis, high gain omnis, and directionals. Three are going to be covering. This is predominantly what we use in UAS right now, and some different antennas that are within these types are known as cloverleaf antennas, patch antennas, dipoles, and a hyperbolic dish. Some of these names you might not be able to recognize, but we use them all. So the cloverleaf is this one right here with these little pedals on it, and it's usually used for FPV, usually in 5 GHz rather than 2.4. A patch antenna, I'll show you what it is later. A dipole is the one that I showed in the video before this. And then the hyperbolic dish is similar to this, where it has a dish behind a omnidirectional antenna. So first I'm going to show you what the gain is, because you saw high gain and low gain. So here's what gain is. So gain is the measure of the effectiveness of an antenna. So let's say you have a light bulb here. This would be act as our antenna. Light waves and sound waves are both the same thing. So let's just say we have 1 watt of power here coming into this light bulb. And a light bulb is omnidirectional. It's an isotrope. So what it means is it sends out its power, or its radio signal, in all directions. And so this has 0 dBi gain because there is the same power input is coming as it is going out. So as 0 dBi has 0 gain. So if you look over here, let's say we put this right here, will act as a mirror. Let's say we don't want to see all the light everywhere. Let's just concentrate our light to one direction. So let's say we just cut it in half, use this mirror. And you have 1 watt of power coming in, so since you're only using half of it, you're going to have 2 watts of power coming out. And this is a 3 dBi gain. And that's because you're having 2 times the power equivalent come out, and you have 2 times the brightness coming out. and I'll show you later with how this it's a logarithm where they figure out what the actual number gain is, and this is how you rate antennas. A low gain is generally around 3, and a high gain is generally around 5 dBi. Okay, so we'll look at the low gain omnidirectional. This is what it comes standard with any controller, and also it's on the UAV itself. It's on the legs here of this 3DR Solo. Omnidirectional is like it is. Omni means 360 degrees, so it makes this huge donut around the antenna. So around the antenna. As you can see here from the top view, it covers the entire 360 degrees, but the thing is, when it goes from the top around to the bottom, it leaves these blind spots on top of the antenna and below the antenna. So these are known as blind spots. And you see here on this 3D model, this is just like a huge donut, and there's just open blind spots here and there. And that comes with this right here, this omnidirectional that comes with any UAV, and then also with the clover leaf. And this one's a little different because it's polarized and it just sends out the signal, but it's the same exact thing as this. As you see here, we have the high gain omnidirectional. This is a 10 dBi gain. As you can tell, it's high. Here, again, the top view gives 360 degrees of area for the omnidirectional. And here you have a high gain because what it's really doing is just sending out the same amount of energy, just in a smaller width. So it allows that donut to be scrunched down and go out a lot wider. And this will help with longer distances for the drone for local areas. Here are just some different types of them. As you can tell, it looks very similar to the other one, but the thing is with this, it's longer, and that does allow it to do this. And finally, we'll look at the directional. This is one that we'll also be testing with the 3DR Solo. It's also one that they use for any number of large drones that are in the military that are contracted. So again, it's a lot different because it's just not 360 degrees, it's only a certain degree angle. So you can see here, here's our top view. You can see that there's no signal coming around out here at all. You're only getting roughly around about 5 to 6 degrees of signal. And what that means is that you're going to concentrate all of that energy going out. As you can see here from this 3D graph, that all that signal is just going straight out. You're not getting anything out here, but this will allow you to get a super long distance. And so many platforms will use this, but behind with this dish and sensor, they'll actually have a rotating bottom mount here and a rotating mount here that controls where it's pointing. And you always want this pointing at the UAV. That way you're getting the strongest signal, because if you're off, even by, according to this graph, by 10 degrees, well then you're going to not have any signal to your drone or UAV. And these back spurts and smaller spurts are just what comes a part of this, because not every single surface is perfectly flat. There's always going to be some kind of gap, some kind of very small area in there that's an imperfection that's going to cause these. And I will be using the 3DR Solo provided by Professor Washburn at Liberty University. I'll be showing you how these antennas work with the omnidirectional and the directional, and show you where they're located on the controller and on the drone itself. Let's get started with the antenna controller. So this is like any drone that you would buy at any store that you or Amazon that you would buy a drone at. So you can see here we have each controller comes standard with 2 omnidirectional antennas, and this allows the antennas will be able to shoot the signal out to the drone. That way you're able to control it in the way that you would like to, and even control cameras and video feeds. On itself, it also has a radio in it, and it has antennas. You can see right there, there's one of our omnidirectional antennas. It's the same thing that is in those other ones, except this one is exposed, and you can just see the little antenna there. It's pretty cool. And there are 2 of these antennas, and here's the other one. So when you have the controller and everything's working good, you'll have the 4 antennas. You'll have 2 on the top, 2 on the drone, and in the next video you'll see how the performance is between the Omni through the directional, and we'll do this at different distances, and I will even show you a graph of how they competed against each other. Everybody, I'm out here at Liberty's rec facilities, and today we'll be just testing the range and the signal strength that we're getting from the two different types of antennas we have, the omnidirectional and the directional antennas. And again, it will be with the 3R solo provided. So right now we'll have the stand here, and I'll just walk out and I'll tell you the frequencies I'm getting and the signal strength that I'm getting. So right now, about 5 feet away, we're getting negative 11 decibels, which is pretty good for omnidirectionals. I mean, you're never really going to be flying this close, but let's just keep going out and just see how the signal changes as we extend. As we keep going out though, for every single time double distance you go out, you decrease in signal strength by an exponent of to the third cubed. So as we keep going, it's just going to keep getting reduced and reduced. And right now we are about 30 feet away and getting a negative 40 decibel reading. And that was a big change from the negative 8 that we had when we were about 5 feet away. And so with the omnidirectionals, right now we are at the peak of the donut. It's the furthest part that is coming away from the antenna. And so right now this is going to be the best reading that this drone is going to get, mainly just because the way the antennas are set right now and because where we're located with the drone. So as I keep going out, we'll get another reading here about 100 feet soon. Just more to talk about. Our antennas are right now, we have two antennas on the bottom of this drone, on the two front left foot and the back left foot. And so having them situated right now are parallel and perfect for signal strength with the controller itself. So now we're 100 feet away and we're getting a negative 45 decibel range. This is still definitely good enough to use. You're going to be flying even a lot worse signal than this, but this will still give you your video feed and it'll still give you complete control of the aircraft, and you will not have to worry about anything at this distance. So the next video we'll look at the directional antennas. What's up guys, we're out here again testing now the directional antennas. You can see here I got the aftermarket directional alpha antennas on, and right now we're getting a reading of negative 10 decibels about 7 feet away from the controller. And again, as we keep walking back away from the controller and as the drone keeps flying away per se, the signal strength is always getting weaker. The good thing about the directional antennas is they give you a lot more range. The reason is because they're only projecting a signal about 100 degrees bandwidth rather than 360 degrees like the omnidirectional. So this focuses a lot of that energy into a smaller area where you should be getting about 3 times better the signal from the controller and from the drone. So right now we're 50 feet away and we're getting a negative 30 decibel reading from the controller. And as we keep coming back, it's just getting weaker and weaker. And right now we're doing a lot better than we did with the omnidirectional as we keep increasing this speed and keep increasing this distance away. Okay, we're about 75 feet now. We're actually getting a very good reading, about negative 37. It's getting better and better, and to the point to where we're getting about to the edge of where the omnis were getting at about negative 50 earlier. Now we're getting a reading of negative 36. So as you can see, even as it switches from about 50 feet to 100 feet, you're not losing that much signal. And as you keep going out and out, you're not going to be losing that much signal as you increase your distance away from the controller. As you saw from the demonstration, we were able to get a lot more distance out of the directional antenna rather than the Omni. But the Omni does good in confined areas, while the directional does good at super long ranges. I did this test, an Omni and directional antenna test, a few days before the other one, just to see how it would react and how it worked. And I actually did not get the same results that I got last time. As you can see from this graph, as I kept getting further, the signal always dies. That's always true. But if you look at the yellow line, it's the directional antenna. It does pretty good. It does a lot better at the close range. It does better in 200 feet. But as it gets to 300 feet, it goes about the same as the Omni. It even gets worse as the distance increases. And you see the Omni, it's a little bit low in area, and it does a lot better at longer distance. You might think, well dang, these two antennas are acting exactly opposite. And there's something that could be affected. One big thing that's affecting this is temperature and humidity. I do not remember the exact humidity on this day, but this just goes to show that not all your software and all your systems are going to work the way you want them to. So here's how signal diffusion and other factors contribute. Here just shows you a graph of how the signal dilutes or diffuses as the distance increases. So let's just say this is a 1 foot. 1 foot away, you're getting your good signal straight from the antenna. You're good. But let's say you go to 2 foot, which is 2R, it diffuses by a rate. So it expands by a rate of squared, of whatever it is squared. So this is 2, so 2 squared equals 4, and then 3R is 3 squared equals 4. It expands out, which gives you good range, but it also thins out the signal itself and has less strength. So as we look here based on the weather, this is just a test that was done in Finland just to see how these signals change relative to humidity and temperature. As you can see here, this is in July of 2014, above 0 degrees Celsius. These spikes during the day in temperature in the red here go up to about 30 degrees Celsius, and the signal received here in decibels is reduced every single time by two decibel numbers. For every single time the temperature goes up and goes down, and the temperature drop is going to be at nighttime, and the peak is going to be during the day. And the signal goes exactly opposite of that as it goes higher, so it definitely shows that the best relative signals are about 15 degrees and lower. And you can see here the humidity just increases, and really the humidity shows that it didn't even really affect it at all. And as we go to December around 0 degrees Celsius, you can see the decibels are staying pretty close together, and this is probably the best area for this particular antenna that they tested. And you see the temperature, as the temperature increases, it drops a little bit, but the temperature is only going up to 6 degrees. And before we got good signals at 15, and so really the temperature does do the biggest effect. And as it will get below in December 2013, below 0 degrees Celsius, going down to temperatures of negative 15 degrees Celsius, you can see the signal jumps as it gets lower, but this is only a very little bit. So really it's only going to be about this much on the graph compared. So the best time to really actually get your best signal is going to be around standard temperature, which is 15 degrees Celsius.